The principal component analysis, or as abbreviated, the PCA, is a process by which we take a complex problem and reduce it to a simpler one. The world is complex. We need to reduce it and to simplify it. And this is what we are going to do in this session, reduce and simplify the world. So let's look at the world. We have many dimensions. For example, each person is living in a specific city. He has a specific profession. He has glasses or not. So up to now, we have 3 dimensions. The city that person lives in, his profession, and whether he has glasses or not. And then let's say that we try to cluster people by their income and try to predict whether there is a connection in between the city that people live in, their profession, whether they have classes or not, to their income. So what we are going to do is to draw the variables on a table and then take samples of people. So we take person 1, and then we assign numbers to the city or to the distance of the city that they have from the Silicon Valley, and we draw it all on a specific axis. And then we take the profession, which is another variable, and then we draw on another axis, and then we take another variable, whether they have glasses or not, and draw on another axis. So without getting into details here, because it's a podcast, you see we have 3 dimensions: the city, the people live in, the profession, and whether they have glasses or not. And what do you think? Which 2 variables are going to have much more effect on the income of people? The city, the profession, or the glasses? So obviously, it's probably the city and the profession. So the PCA is supposed to identify this. It's supposed to tell you at the end of the process, you just like run the process like a duck. Step 1, step 2, step 3. It's very dry process. You just go through the process, and then at the end, you would plot some diagram and you would say, okay, city and profession are the most basic ones. These are the 2 most important. And imagine that we didn't have just 3 variables, but we had 300 variables, 1000 variables, 1 million variables, and we'd extract 2 or 3 most important variables that affect the income. This is the PCA, the process, the principal component analysis that allows us to get from the components into the principle of what the basic is. So basically, we take a look at the dimensions, and we are creating what is called a line or an axis for each such dimension. So if you had 2 dimensions, then you create 2. If you had 200 dimensions, then you create 200 lines. And these lines, these dimensions are called the PC. So you have PC1, PC2, PC3 if you have 3 dimensions. And then we look at the points that we draw on the dimension. So if you see all the points are on a specific axis from its beginning to the end, and this means that this axis is very important to our problem. So we move on with processes such as creating eigenvectors and other curses. And with this, we basically try to identify what is the component that has the most effect on our prediction and on our value. So by the end of this process, we have the variance of each PC. So we have the variance of PC1, the variance of PC2, the variance of PC3, and we sort them from the largest to the smallest. So if you would see that the variance of all these axes, the city that they live in, whether they have glasses or not, whether they lack MacBook or not, if you see that all these variances have like the same height on the graph that you have finished, that this means that all these variables are contributing the same to the income of this person. But if you see a degradation that the first variable has a very high variance versus the second one versus the third one, then you can take the first 2 ones and then draw a plot only based on these 2 items. So you see, so we make lines. We make a line for PC1, then we make a line for PC2, and there are many technicalities and other dry stuff that we run like a duck. For example, we tilt the graphs so that the graphs are aligned and not just graphs with some angles. And then after we get to the 2 dimensions, we look at the graph that we have there all the observations, and then we could see clusters. We would see clusters if the variance is very high, so you could see how it affects the things. Basically, by the end, when we get the eigenvectors, we get like something like 0.4 PC1, 0.3 PC2, 0.1 PC3. So you see that PC1 and PC2 had 0.4 plus 0.3, which is 0.7 out of 1. So they are very important. So we can take these two. And to get to more details, the process is this. In step 1, you take the data and take the data for all the variables and create a line. You create a line for PC1. What is the line? If you have many dots, for example, if you print the distance from the city as opposed to the income in the line for PC1, then you try to find the line that is best fitting. And there is a process for this. So there is a process to find the line that best fits all the dots. So if you have dots that are going from the left to the right, you would find that this process will get you to such a line. Then you do the same thing for PC2. You find the best fitting line. You start tilting them so that the lines are not just, because it doesn't really matter but it's technical. So then you draw the same thing for PC3, and then you try to find which ones are having the most variance in comparison to the rest. You do this with the eigenvector. As we said, the eigenvector is the composition of the unit vectors that we get from the lines, and we get a prefix for each PC, and the two highest prefixes are for us the two principal components. Okay, so these are the two principal components that we are going to get. So this was a very brief introduction into what is PCA, principal component analysis. In this process, we take variables such as the distance from the city, variable 1, whether the person has eyeglasses or not, and what is the car type of this person. We compare them to the income, 3K, 4K, 5K. We draw lines for each such variable. We do some manipulation on this. We try to find the best fitting line. We get into multiple dimensions. We get to the eigenvectors, and from the eigenvectors, we get the prefixes. And the two, let's say if we are interested in reducing it to 2 dimensions, we take the two lines, the two pieces, the two principal components that has the most variance. So I think this was very interesting, and see you next time.